I saw this question on YouTube, which is done by Feynman's technique. Now, I have a different way of doing it. It's a simpler, and I would like to share with you. Now, I consider this is the imaginary part of a complex number. So this one is equal to imaginary number, imaginary part of x squared and e to the negative x squared and e to the I x squared dx. Right? This complex number imaginary part is this. Now then, this one is equal to imaginary part of this. I can combine them. This is e to the negative 1 minus I x squared. Right? It's combined. Dx over x squared is the derivative of 1 over x. A negative. I take negative outside. Good. Now then I can use by parts. This one is equal to negative imaginary part of uv. uv. U is this. V is that. From 0 to infinity. Minus become plus imaginary part of that integral, which is 1 over x from 0 to infinity. And this derivative with respect to x, that will be e to the negative 1 minus I x squared multiplied by the negative, this derivative, right, with respect to x, which is a 2 times 1 minus I x, yeah, dx. Wow, I hope it's right. Okay, then this limit, when x is approaching infinity, this is easy because this is 0, right? The whole thing 0. When x approaches to 0, e to the negative 1 minus x squared. When x approaches to 0. Now I consider this one is e to the negative x squared, right? This is what? This is e to the I x squared over x, right? Yeah, imaginary part, huh? This one approaches the imaginary part, x is e to the x squared. This is cosine x squared plus I sine x squared. Imaginary part, therefore, this is gone. This is approaching to x and sine x squared. Yeah. Now, when x approaches to 0, I can multiply by x and x. Right? So when x approaches to 0, this limit goes to 1. Because sine something over something square. Sine something over something. When something goes to 0, this go to 1. So this one goes to 1 as x approaches to 0. This one approaches to 0. So it's approaches to 0. The whole thing approaches to 0. So this one's approaches to 0. Now left over, this x cancels with that x, right? becomes a negative, the negative 2 imaginary part. I take the constant out, 1 minus I, and the integral from 0 to infinity, e to the minus 1 minus I x squared dx. Wow, finally a little clearer. Now this one is equal to negative 2 imaginary part of 1 minus I integral. For this one, I can reorganize as negative square root 1 minus I x together square. Then this one is equal to d 1 minus I x, maintain equal sign, divided by this, right? Then it's equal. Yeah. Now we have a Gauss integral, right, of 0 to infinity e to the negative something square d something is equal to half root pi, right? That is a famous integral. So this one is equal to negative 2 imaginary part. Now this one over that one is a square root 1 minus pi. That integral, as I showed, this is equal to half root pi. Wow, this is equal to negative root pi imaginary part of 1 minus I. Wow, it's much better. We just take the imaginary part of this complex number times this is our result of the integral. Now, how to find this one? It's easier. Right? This is 1. This is 1 negative I. So this is the complex number we are talking about. And the argument is a negative quarter pi. The modulus is equal to root 2. Yeah. Yeah, I forget half square root, huh? Gee, always forget something. Square root. So this number, complex number, square root. This number, square root, imaginary part. So it's negative imaginary part of this number is root 2 cosine negative quarter pi. For cosine is same. Positive, negative, the same for cosine. But for sine is minus I, right? Sine quarter pi. Okay, good. So I take imaginary part. So this becomes, no, there's, I forget this one. Square root, right? Square root. This one is equal to and square root 2, right? Square root 2. This is gone. Imaginary, and this is negative sine pi over 8. Yeah, finally this is equal to square root pi square root times sine pi over 8. Yeah, that is the result. Good. I use a conventional way by parts. Okay, the only things that I'm using Gauss integral. Yeah. Thank you.